to achieve this. One is top-down approach, and other is bottom-up approach. So, as I said, that when we start from the smaller elements and smaller species and join them, make them a quantum structure. So, this is bottom-up approach. Another thing is that we start from the bigger system and start reducing it, and we get this quantum structure. Then it is a top-down approach. So, I discussed last time the method that is known as the electron beam lithography. Electron beam lithography method, and in that method, I told you that we start from the quantum well, which is already a film is deposited on a substrate, and then how we reduce it, how we shine the surface with the help of a template or with a shield in a limited area by electron beam, and then we by choosing suitable chemical, we etch out the region which has been exposed, and then again we put a mask, and then again we reduce it, and in that way we get a quantum rod, or we can also get a quantum dot depending upon the kind of template that we have used. So the whole process is very well described in the book. I have given the reference of it, and if you will desire, then I can also send the whole article on that. And the book I have prescribed is Introduction to Nanotechnology by Charles P. Pulley and Frank J. Owens. So this is the book in which chapter 9 deals with the portion which I'm going to take. So as I said, that this electron beam lithography technique has been properly described in this article, and I have also given the outline of this, so you can uh, go through it, or if you have any doubt or any question, then you can certainly consult me. Now the second method that I wanted to discuss today is the deposition techniques, like what we call as the molecular beam epitaxy, MBE. This is a very sophisticated method to prepare quantum well. And I will tell you that how molecular beam epitaxy looks like with the help of some schematic. I have sent the schematic. You can look into it, and when I will be describing, then I will be taking help of that figure, which is I have already sent, and you can see it, a schematic view of the molecular beam epitaxy. Before telling what is describing the method, I will tell you what is the meaning of epitaxy, because it may be new for you. This epitaxy means that if there is some underlying crystalline surface, and if some other material is getting deposited on it, then the surface structure will be mimicked by the material which is being deposited. So there is a orientation relationship between the surface structure and the film which is getting deposited. So if it happens like that, then it is epitaxial growth. Generally, what happens that when you deposit a film on a surface, it is not epitaxial because it will be polycrystalline. There will be so many small grains which will be deposited, although it will look like a film, but that film will not be a single crystal. This will not be this will consist of so many grains. There will be small grains, and because of that, this is not a epitaxial film. Sometimes some of you might have occasion to deposit film, and you might have noticed that it looks very smooth or something like that, but that film is not epitaxial. For epitaxial film, there should be a proper orientation relationship between the substrate and the film which is getting deposited. Then we say that it is a epitaxial film. I'm giving you example. Suppose that there is a surface, suppose it is sodium chloride or suppose it is silicon or something, silicon, and it is having the surface, and the surface corresponds to, say, one type plane. Suppose it is 111 plane. Yeah. Miller indices is 111. And another film which is getting deposited, it is also having a one plane throughout. That means the plane may be of 111 type or 110 type, but the complete film will be having the same orientation. Then you can say that it is a epitaxial film. Huh? So this is very important to understand the meaning of epitaxial film. Hmm? So on the on because of this kind of film that we get, this method is known as molecular beam epitaxy. So how molecular beam epitaxy, mm, this arrangement, how is done, this I will be telling you. I will be when I will be describing the molecular beam epitaxy. Now you see that at the very outset, at the very beginning, let me tell you, it's a very expensive apparatus, very expensive. Several crores of rupees are required for this kind of apparatus. But then what we can appreciate is the kind of arrangement, the kind of instrumentation that is done, that has been done in this equipment. You can just see, I'm referring to the figure which I have already sent, and you can see that figure. Unfortunately, I am not able to show you here on slides, but of course you can refer to the figure, and you can see that there is a chamber. This chamber, big chamber, is made up of steel, very high quality steel. This chamber is made, and then there are several ports. And let me describe one by one these ports, because for example, you have effusion cells. Yeah, if you see in the figure, it is written effusion cell. There are four effusion cells shown here, but there can be several. And in each effusion cell, the material that you want to deposit, that is that is put in that, and it is heated with the either with the help of some heating source, maybe electrical source or some other source. So there is a so these effusion cells will contain, for example, if you want to deposit gallium arsenide, then in one of the effusion cell there will be gallium, in another cell there will be arsenic. If you want to dope it with silicon, there can be there can be some silicon, and so on. So these are different effusion cells through which the material which has to be transported, which has to be put on the film, that will be put there, and that will be heated. It gets vaporized. Then there in the opening region there will be shutter. There are shutters, and these shutters are very much electronically computerized, computer controlled. That means they will open, and they can again get shut down electronically. And so you have very efficient way of using shutter, so that you can check the growth. In the same way, you can just see that there are pumps. Actually, these pumps actually are very much required to evacuate this, to have very high vacuum. For example, to the range of 10 to the power 8, 10 to the power minus 8 Pascal. Huh? So this is a very 10 to the power minus 8 Pascal. So you have to have because you know that it is directly related with the mean free path of the molecules or atoms which are getting deposited on the substrate. So that's why there is a pump, and you can see in the figure the pump which is shown. If you have to make a schematic, you may not make such a. You can just show that these are the locations where the pump and other things are arranged. So there is a very nice pump here, and then you have a substrate holder, and it can be rotated from outside. In the same way, you can have, for example, you have to also monitor the the structure of the film. So, as you know that we are talking about the epitaxial growth. Epitaxial means that the whole film will be a single crystal. It will not be a polycrystal. So if it is a single crystal, then how we know that it is single crystal? So we will have to make use of a technique known as reed. What is the meaning of reed? RHEED. Reed means reflection high energy electron diffraction. So this is a reed technique through which we get the diffraction from the film, and then there is a fluorescent screen. Only through that we can see the scattered beam, or say the diffracted beam. So we see the single crystal pattern, and so we are assured that it is a epitaxial film. So as I said that epitaxial has to be a single crystal. Hmm? So you can recognize, you can realize the difference between polycrystal and single crystal. And what am emphasizing here is that the whole film has to be a single crystal. Only then it is a epitaxial growth. Then you can see that there are, of course, windows there through which you can see that whether the deposition is taking place or not. And there are other details here through which, as I said, that the vacuum level of the chamber is of the order of 10 to the power minus 8 Pascal. And you, from your thermodynamical or kinetical calculations, you know that the mean free path will directly depend upon the pressure, how much vacuum is there. So at this level of vacuum, 10 to the power minus 8 Pascal, the the mean free path will correspond to the mean free path of the atoms will correspond to several meters. Huh? That means, what is the meaning of mean free path? You know that without having any collision, it can move from one region to other region up to few meters. So it's a and the chamber is less than half meter, maybe less than that. So you can just imagine that the atoms which are going from a fusion cells, they will, without interruption, without getting deviated, they can directly come. They will touch the. They will come to the surface of the substrate. I have also explained you the meaning of substrate. Substrate is the material, single crystal material, where the film which is getting deposited will be deposited. Okay, so this is the substrate. This substrate may be single crystal gallium arsenide, or it can be mm, um, silicon, single crystal silicon, or something like that. Huh? So you have substrate. So as I said that this is and the deposition rate is very, very slow. You imagine that it will be as slow as if a few layers will be deposited in 1 hour or something like that. So very controlled deposition. Growth rate of the film is very, very small, of the order of, say, the few angstrom per hour or something like that. So it takes several hours to get a proper quantum well. Huh? So as I said that it's a very sophisticated technique. Uh, but very expensive. But so there are many advantages and there are disadvantages, huh? uh, that I will be discussing. But let me also point out that sometimes you have to have doping, either P type or N type. Suppose it is gallium arsenide, you want to have N type, you have to dope it with silicon, or for P type, you have to dope it with beryllium and so on. So there are many dopants, and in if there are several effusion cell, and in that effusion cell, you have to put these materials. They will also get evaporated, and then they will be getting deposited. They will be mixed up with the beam of these atomic beam, and then they will get deposited on the surface of the substrate. So in that way, as I said, that it's a very, very controlled way of deposition. I have also told you the read technique. Read is a very important technique, high energy. Read means reflection, high energy electron diffraction. So read, RHEED. So this read technique is very unique technique. And at least if you can't see the exact equipment somewhere, you can look into the read pictures. In some textbook or in some research papers, where they will show you the single crystal pattern. And single crystal pattern is representative of the complete single crystal. That means it's not polycrystal, it's not ring, but very, very well defined diffraction spots, which indicate the reed, which indicate the formation of single crystal. So these thin films, which are epitaxial, they are actually single crystals. Throughout, there is no grain boundary, and that's why they are a single crystal. And that is the meaning of epitaxy. So this is way, as I said, that some of you uh, may get chance to work with such thing, that will be very a thrilling experience, because there you will see the very very sophisticated kind um, uh, of arrangement, huh? Where on one side you are having a deposition of the film, you are monitoring the pressure, because pressure has to be very very low, so that the mean free path should be as longer as possible. And I just said that that is done by several vacuum techniques like getter ion pump. And then you have, say, the getter ion pump. Let me just explain that actually in getter ion pumps there are metals which get ionized, and then they absorb, they react with the gas, and then they get deposited. And then in that way, the remaining gas which is there, it is washed, it is absorbed by getting process. And that is why getter and pump, gettering process. And before that, of course, there are, say, the turbomolecular pump and other kind of pumps, which uh, actually help in having creating a very high level of vacuum, huh? So I just said that this, as I was pointing out, it has, this technique has several limitations. The limitation is that it's a very very expensive method, very very controlled but slow growth. So it's much more suitable for research and for the further development. And one has to have some less expensive and faster technique, and that technique we call as MOCVD. M means metallo organic chemical vapor deposition, MOCVD. So MOCVD is another technique through which one can get these films which are epitaxial, which are single crystal. Because please mind it, that once it is polycrystalline, then its properties will be deteriorate, its property will not be suitable for making quantum structures, and therefore a great art is required for getting MOCVD deposition. Huh? So, well, let me just tell you in another figure, I'm referring to another figure where the schematic illustration of the arrangement is shown. What kind of film you are making? I'm just taking the example of gallium arsenide. So some compound of, say, the arsenic, organic compound, and some compound of, say, the gallium, for example, TMG. TMG, that is a trimethyl gallium. Trimethyl gallium is TMG. So you choose this organic compound. You also, you have to take arsenic tetrahydride, ASH3, and the reaction I have not shown here, but I will send you I will send you the picture of this. The reaction that takes place is that gallium uh, um, tri, um, trimethyl gallium reacts with the arsenic uh, trihydride, and then they are in gaseous form, and then they combine to give gallium arsenide that will be solid, and there will be CH4 gas. So the CH4 gas will be coming out. So this is the kind of reaction that takes place in the reaction chamber that we call as the reactor. So this reactor actually is the place where this kind of reaction takes place at high temperature, nearly 700 to to 800-degree Celsius. It's a very high temperature. It's a rather high temperature, and then the reaction gives rise to the gallium arsenide, solid gallium arsenide. Now let me explain the schematic. How this with the help of schematic. Actually, what happens that in order to have say somewhat unreactive atmosphere, we flow hydrogen. So hydrogen is flowing through, and there are valves actually, and they regulate the flow of hydrogen that with what flow rate the hydrogen will flow through the reactor. Then in another vessel, in another cylinder, we have arsenic trihydride, and that flows. Actually, here the carrier gas has been taken as hydrogen. What is the meaning of carrier gas? Actually, this carrier gas will carry the material to the reaction place, and that is why one has to use some kind of carrier gas. And in this case, hydrogen as a carrier gas has been taken. Then then you have say the metal organic compound, metal organic, that is why its name is metal organic chemical vapor deposition, MOCVD. So you have some metal organic, and in this present case it is TMG, trimethyl gallium. Okay, so it is in the form of some liquid. It is put in some vessel, and again by heating the vessel, by so that the evaporation takes place and vapors of say the trimethyl gallium start flowing in the pipeline. And so what happens that they enter the chamber, that you can say reactor, and there you have some substrate, and on that substrate the deposition will occur. Now this method, and then after reaction, the gases which are unutilized, they will be pumped away. They will they will be coming out of the chamber, and for this one has to make use of a pump. And so with the help of pump, you see the gases which are unutilized, they will be coming out. And so this method is a rather faster method, is a rather it's less expensive than in the case of say the MBE. Here you can just see that we are not in situ, while deposition, we are not monitoring the structure and other thing. This may be done after deposition, but in MBE, this process is there. This possibility is there that you can see the structure when the film is getting deposited. So so I said that it is a less expensive method, and you have to choose suitable metallo-organic compound for the depositing metal for the and so I said that this can be this will be rather less expensive, and then you have to, if you want to dope your film, then you have to choose suitable compounds. For example, if you have to put antimony or something, then you have to choose trimethyl antimony. Or for aluminum, if you want aluminum doping, then you have to use trimethyl aluminum. And in the case of indium, you have to use trimethyl indium, and so on. So these compounds, these suitable organic compounds, has to be used for 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 deposition and for grouping of the this kind of uh, in this technique MOCVD. Now they have hybrid. They have some hybrid where they method where they can make use of some aspects of MOCVD and some aspect of say this chemical vapor deposition and they have so there are some more some more advancement in this technique where because you see you have to make compromise between the cost of production and the quality and so on. So because you don't want to push the cost up, and so that's why. But at the same time, one has to check the quality of the film because they will be very sophisticated. Quantum well, they are this. You know that quantum well means that there is in one dimension there is a reduced thickness and then you have other two dimensions which are bigger, and so this is quantum well. And for quantum well you have to have very high quality of the film, and so that's why. Now there is a last figure which I have shown, and you can just see that shows the growth. That means that the growth rate versus the reciprocal of temperature. What is this temperature? Temperature of deposition of the film. So I just said that by changing and this is done in the reactor, in the reaction reactor. And what happens that if you change the temperature of the reactor, temperature of the surface, then what will happen that the growth rate, what is the meaning of growth rate? That means the rate with which the thickness of the film is increasing, that is the growth rate. That means here on the y-axis, growth rate is written micron per hour. Huh? That means micron, 10 to the minus 6 meter. Okay, so that's the so micron per hour. And on the x-axis you have reciprocal of temperature in Kelvin, or on the upper side it is given in Kelvin directly. So you can just see that when you are lowering the temperature, that means the graph is shown that it may, in the case of, say, the gallium arsenide, suppose you have, say, the gallium arsenide surface 100, that you know that that's the orientation, Miller indices, okay, the plane which is growing. So so you can just see that in the beginning it starts when you are decreasing it at very high temperature. The growth is slower, but then at some intermediate temperature it becomes constant, almost horizontal, and then at lower temperature it decreases. Okay, so you can just see that this is the kind of growth rate. So one has to consider the suitable temperature so that there is a constant growth rate. There is a whatever growth rate is there, one has to see that it's a uniform growth rate, and so this is the dependence of the growth rate on temperature. So you have to manage, you have to see that a suitable growth rate is depending upon the temperature, and so one has to maintain it. So as I said that these are the very these are very important two techniques. That there are so many other techniques which I have not discussed. That is, but just to give you feeling that how quantum well is created, how quantum well is actually produced. I have given this example. Of course, when you are using the electron beam lithography, then you start with the quantum well. So you have to get the quantum well from the experiments like this, and then you can make use of electron beam lithography. So these are the three major techniques which I have tried to summarize, which I have tried to tell you in this lecture. And the proper references, for example, the one I have taken the portion of electron beam lithography, no, from molecular beam epitaxy, MBE, and the chemical MOCVD. This I have taken from the book of, say, Lutz. Lutz book. What is the name? Some of you might be using solid state physics by Eibach and Lutz. There is a book, Eibach, uh, BACH, BSc Ibach and Lutz, Lutz. Lutz. This is they have written a book on solid state physics, and there yeah, you will find the description of MOCVD and MBE. MBE is also described in other textbook. For example, you will get it in solid state physics by Byrne. There is a book by Byrne in the library. You will get it, or maybe you may get on your internet, I don't know. But this book by Byrne, hmm, this also contains this molecular beam epitaxy, but that book doesn't contain the chemical deposition technique, MOCVD. So MOCVD you will get in Lutz book, Eibach and Lutz. So you look into that, and in the next lecture I will be telling you what we mean by, say, the size effect, and then dimensionality in case of uh, what is the significance of size effect and what is the significance of dimensionality in case of, say, quantum structures. So this I shall be discussing in the next class. So with this, I'm stopping here. Okay. Or if you want to ask anything, please ask. Any question? Any question? Please ask. I will also understand that you are listening. That's why I'm asking that whether you have followed something or you want to something. Hello, any student? सब शांत है, सब कहीं चले गए क्या?
No, sir, we
Hello.
are.
हाँ, I'm okay. So Chirag, हाँ,
Yes, sir.
you want to ask something?
No, sir.
Okay, okay. You see, you may be surprised that why we are asking such technique. The thing is that we should have some feeling that, you see, that when we say a quantum well, it's not so simple to deposit. I want to make this point clear that for making these structures, the kind of sophistication in the equipment that is required, and that is the idea to tell about the molecular beam epitaxy. Unfortunately, this facility is not there in our, I think, in the whole university, I should say. Huh? But of course, I'm very sure that at some point of time, at some stage, you will be getting opportunity to work with such instruments. So that's why you see it is a kind of familiarization with the kind of equipments which are required for the preparation of these quantum structures like quantum well, quantum dot, and quantum wire. So that's why I have given these three techniques description, just to give you the feeling. Huh? But of course, I have given you the sufficient reference. But if you get any problem, then I can send the whole description from here itself. Okay, so you can read it. Okay, it's all right.
All right.
Huh. So if you are getting any difficulty in terms of literature or in terms of understanding of the few points, you can contact me. I will help you. Okay, but I will at the same time I will say that each topic you should prepare it by yourself by looking into the details of it. Okay, that will help you. All right.
Yes, sir.
So, so if there is no question, and I hope that you might have understood something, some portion of it or something. I will stop here, and we will meet next time. And at that time, I shall be discussing size effect and dimensionality. What is the meaning of size effect and what is the meaning of dimensionality in case of quantum structures? This I shall be discussing next time. Thank you. Thank you. तो अब क्या करें?
Thank you, sir.
Okay. This